This is our fourth lecture. We will talk about some information retrieval and classification tasks. For those who actually do it in your work, on your research, has probably some background knowledge and basically know how to do it. For those who not yet tried, I encourage you to try, and I'll try to speak in a very basic way and won't go deep in details again, because if you want details, you can go to Wikipedia or read the articles and have reference for each. So it shouldn't be a problem. If you really want to understand, it shouldn't be a problem. So, for those who was not yesterday, what did we cover? We covered some social media sources. We just talked about how different data is. We mentioned that microblogs is a completely different source. It's not just like pure text as before. It's have a certain structure, it's certain vocabulary used. So all the common natural language processing techniques are not really applicable to it. So we also wasn't talking about different textual data representations. So we were talking about possible topics you can extract from text, and also we're talking about different combination of terms and grams. So it's features that represent our documents, so further we can work with it. And except this, we also have two more sources of data. We were talking about image processing and about image source, where we want to work not with textual data but with image. So we was talking about different image data representations like edge histograms and color histograms and some shift features and even some high-level image concepts. And besides this, we also have the location data, which is very widely available now. We even have these location-based social services like Foursquare. And all these services provide a very rich content. The main point of this content is not just geolocation. It's actually very nice image semantics for every point. So when you go to a certain place, you actually know what exactly this place is, not just physical location of this place. And we come to a conclusion that all these sources need to be considered when we do data analytics. It's not enough to do just textual error, they're actually passing. And there's still quite a lot of papers doing pure on text, but I guess for multimedia, for social media, it's really not enough. And as an example, I was recently talking to head of R&D department of Bloomberg. Not Bloomberg, right? It's a very big analytics company for finance, for investment. And even they analyze not just textual data from news feeds and so on, but now try to analyze the speeches of the people. So try to get some info from speech and after that produce some news feeds for their clients faster. I guess further in Saturday, Prof. Center, head of our lab, will talk more about what currently changes in the social media field. So I guess he'll talk about videos and about other types of data like sensors, which is quite important. So by now we're supposed to understand how different types of data is converted to feature vectors. Feature vector is basically just a number of values, a number of real values. So it could be distribution among different categories, or can be some representations. We don't really know exactly what's that, but we know it's actually related to category we try to predict, or the task we're going to solve. So in the beginning today, we'll talk about text, and we'll talk about information retrieval and classification. Regarding text and microblogs, all the techniques which are applicable there are actually applicable to other types of data. So I will focus on text, but you need to understand that all these approaches can be used in the same way with a minor modification for image data, for sensor data, in case if you appropriately preprocess it. And in fact, feature engineering for application, feature engineering sometimes even appears to be more important than the actual model that you use, because features are related to the field you are modeling, right? It's related to the data. If you're able to extract some meaningful representations of data, then your model can easily learn some relationships that affect your final label and try to predict. But even if you have a very fancy model, but your feature representations are not very useful, not really correlated with the data, then you may not get nice accuracy. So that's why I support all research based on real data sets. That's why I give you real data sets in this assignment rather than something generated. So the purpose is describe some information retrieval and briefly introduce some basic machine learning approaches for those who don't know yet and we want to refresh. And we're going to talk about differences between retrieval and classifications. And later we'll talk about some evaluation measures. I guess evaluation measures maybe we'll cover in the next lecture, but wherever. And yeah, everything here for a certain type of people is background knowledge. So if you have some information review or machine learning background, you can relax. Maybe give me some suggestions about your opinion about certain approaches I will talk about. You may know something I don't know, or you may have some interesting research in your background that you can consider. References I like this. The last one is the most interesting thing. It's quite easy to read book. I guess you can download this book, read the whole book, and after that you know quite enough at least for implementing real-world machine learning systems and to understanding how it works. It's in English, but it's a really simple book. So they try to explain it for people from different disciplines, not just from math background. Of course, you need some basic math knowledge, but it's usually easy to read, so I recommend it in case you're interested. Slides are all available in my webpage. Okay, here already you cannot see because they erase. Yeah, maybe I need to write again. Didn't manage to process all the videos that I shot yesterday, but like after conference, maybe in 2 days, I guess I also upload everything so you can see the lecture that you didn't see before again. Yeah, so it's all here. The data set, there's also reference in that web page and our following slides. So we'll discuss the data sets and issues about it later a little bit again. So let's recall some knowledge from previous lecture. Actually, what is a free text? What do you think?
Preprocessed text.
An example where we can get free text.
Non-structured text, for example, Wikipedia articles.
I wouldn't say Wikipedia is really not structured because we have many examples of something really not structured. Yeah, but basically all this text they are working is more or less free text. Some of them is completely free, it's very difficult to work with. And some examples are more structured, easier to understand, easier to process, but so it's still free text. So example is just like this sentence. And for information retrieval, to be able to do search of text documents by query, we need to index this text somehow, right? So we need to map it to some structured knowledge And it's not like a database when we already have the tables or just such. So the nature of indexing information is really different. If you're curious, you can go read about Lucene. It's a state-of-the-art search open source engine. You can actually see how it works and read documentation and even use it for your projects. In fact, it's used in many applications when people need to implement search for their projects. So what we need to do? We need to extract some distinct features, representative features. And for retrieval, we need to distinguish a particular document from the rest. While in a classification, we need to find the group assignment for every document. So is it similar or different? How do you say? Any difference between these two tasks? Can one be generalized to another? What do you say? Or is it the same? Okay, I'll go back to this later when we can see everything. So we have different types of features, right? Like the LWC that we discussed yesterday, and topics and ranks and so on, so on. Different feature representation of text. And actually any other information. And it's actually interesting, maybe, I mean, some of you maybe argue with me, but in fact, most of the really large scale text analysis systems are term-based. Just because if we try to do something more complicated, it will take too much effort to analyze. So actually, in fact, they're all term-based still. Yesterday, there were some people from my classmates that actually work with the big data. They say they sometimes use LDA for certain tasks, but it's not like so often. Which basically proves the same thing, right? So, and in information retrieval, the system usually performs some pattern matching. So basically, they compare two vectors to feature vector, and there's no any semantics considered. Or, yeah, always like a very few semantic considered for this. So, most of the cases, information retrieval just stupid matching of two vectors to try to find the most closest one according to some similarity measure. And this is sometimes very general. So, in this point of view, classification is similar. I mean, all the large scale systems also are quite silly working, and they work quite well in case if you have a lot of data. So actually data give us a lot. If you have nice big data sets, if you work in such companies, you can do very nice just with simple techniques and with features, with simple features. So retrieval is basically follows the process, and we have a query. We need to find the document that matches query. So in classifications, we need to find the document that matches some class. So we have some class, and we need to match this class. So in retrieval, we have top K document that is similar to document, query document. In classification, we have documents, and these documents assign some classes. So what's the difference? Any ideas? Again, are the same. Maybe you can think the term.
Even different things. It's like in first case we have a query, just for some example, and in the second we are given a whole class.
But it doesn't change the whole principle.
Classes is fixed.
Yeah, that's correct, but
query may change from session to session.
okay, let's say yeah. Okay, that will be one difference.
Classification is quite a cognitive thing. So you try to separate different types of documents, and then you work with each class next time you maybe can use different queries, on different conditions, something like this.
Any psychological insights?
Yeah, there is one psychological insight about this.
You need to leverage on your knowledge, it's quite interesting.
Our consciousness works with so classification is just basic cognitive thing for people, but we classify things differently from computers. For example, Eleanor Roche, psychological scientist, she made an experiment asking people, giving people some kind of phrase, and so she expected them to answer true or false. So they answered with the computer. The phrase was really simple. For example, pigeon is a bird, or ostrich is a bird. And so she, of course, almost everyone, I suppose, answered yes, so true for these phrases. The thing she measured was the time. And so she found out that the time for the phrase pigeon is a bird is less. So this meant that pigeon is more birdy than ostrich for most of people. So people classify information with the stereotypes, and if something doesn't match the stereotype, it is on the border of this classification, so near the border, far away from the stereotype.
Maybe just because pigeons are common.
Yeah, of course. So for example, if we, she made this conclusion that, for example, if we ask people in Africa, maybe we'll find a different...
you have more training samples. Pigeons which are
and she made such experiments in Asia, and where, for example, there are no, I don't know, there are no sparrows or some common birds which are here. But yeah, she found out that, for example, for these people, sparrows.
Region dependent, right?
Yeah.
Yeah, I mean, it's quite obvious actually. That's why we also try to consider different regions. That's why a data set I provide is actually from 3 different countries, and I expect to see different performance and different interest insights you can get from there. That's because people communicate differently, they use different topics, and so on and so on. But the simple one is much the patterns, right? So we count the number of words, and we call it body words. So each document is represented by distribution on the top popular words. And we also have some insights that we actually need to select these distinctive terms between each other. Because if you use all the terms, some of them will be noisy, or not noisy, but just not useful. Something we discussed last time. And in fact, we come up with it by eliminating some high-frequency words, which we call stop words. And then we use the remaining terms from indexing. I won't touch indexing itself, but here we already have quite structured representation, so indexing will be similar to what you will learn from database course and so on. So this is like just one of possible stop words, but there's many. It can be language dependent, and field dependent, and application dependent. So you can find a lot of Google and wherever. So what we found that precision is better served by features that occur frequently in a small number of documents. Precision basically is a fraction of retrieval instances that are relevant. So we get some list of instances and we count how many of them are relevant. So this is more important for us to have some frequent terms in a small number of documents. Why is it important for precision? And just because in some documents we use that probably belong to some topic, we have a lot of similar words occur many times. And if we don't have these words in other document, for us it's very easy to distinguish our query document and we distinguish the target document, the relevant document among all others, just because this document will have a very high frequency of certain words. So if you just use a back of words model, you can easily retrieve these documents. So, and this can be used, we can leverage on it by using the inverse document frequency, so-called IDF, which is, how many of you know what is IDF? So it's actually inverse document frequency. So in the top we have the total number of documents in collection, and in the bottom we have total number of documents when this term appears. So we basically see the proportion of whole documents and documents with certain term. So that will give us a measure how often a certain term appears in certain documents but not appears in others. So this is important for precision.
Why is it logarithmic?
Just to smooth it. They use actually different types of inverse document frequency. About these ones. Numbers can be quite big, so sometimes it makes sense to make it logarithmic. But yeah, whatever is not so important. The main thing you need to understand is just that the thing that is a proportion between all documents and those where this term appears. So this is an example, right, of IDF for different situations. For example, we have some documents and some sim alpha appears in 100 documents, and IDF will be like this. Beta appears in 500 documents, and IDF will be like this. And 900 documents, it will be like this. So you can see, right, for case when some alpha, some word term appears in some document, many times, but if we have few documents like this, so these documents are more representative in terms of precision, right, for retrieval. The IDF will be bigger as compared to when we have some term that appears almost in all documents. So this is not too useful for us for precision. And yeah, and if it's logarithmic, you can get some small numbers, so it's nice. You don't want to normalize somehow. And TF, term frequency, helps in recall. So recall is a fraction of relevant documents that are retrieved. So basically recall is out of all the relevant documents, how much we manage to get. Doesn't matter how much we get irrelevant. In this measure we count how much relevant documents in our output. Even it's very noisy. So we just count how many pickups from the whole set. And here is term frequency is important. So in the denominator we can see the maximum row frequency of any term in the document. So why term frequency important here? You know what is term frequency, right? Term frequency is basically the number, how many times this term occurs in the current document. You can see the measures there. Again, this 0.5 and so on is just like one of versions of term frequency. Not necessarily be like this, there can be different variations. So why term frequency important for recall? I think it's quite obvious, right? Because our aim is to get as much relevant documents as we can. So we can use term frequency of each term in document to get as much as we can, and we don't really care how many of them will be irrelevant. So you'll get all. So in fact, we can get very high precision and very low recall, or opposite. And in both cases, we won't be really satisfied. The combination of these two give us very famous TF-IDF weighting scheme. So, which is basically the multiplication of TF and we extract some word counts from the document, right? And we also have some stop words I extracted from there. So we won't use it. Just remove it by stop word list. And finally, we have these terms extracted from there. So, what problems do you see in this list? I guess yesterday we mentioned already.
Word forms, with words and word singular.
Yeah, so it's different form of the same thing, right? So what we can use for it? As one of ways, we can use stemming, which is normalization by suffix or by some vocabulary.
Yeah, lemmatization.
Yeah, because we can use lemmatization with more complicated techniques. But however, we need to normalize it somehow, right? So we'll finally remove these, and we'll get these, and we'll make it the same. So we'll treat them as the same word. Our next problem is the terms are having different grammatical variants. This problem we deal here. So, but at the same time, we need to reduce number of terms, words, by perform stemming. And also, it changed its, remove the variance between words, so we can treat the same word in singular. So since we can identify similar words, we can do better retrieval and classification later. And most stemming algorithms, as I said, are based on suffixes. So sometimes when we perform stemming, it's actually decrease the performance just because the word will lose its meaning. So yeah, so we need to be careful about it. And we can have some steamers, for example, the smile stemmer. Just go over it, how it works. It's all simple rule-based techniques. So if you put all together, we have to extract some unique terms in documents. It's important that this be unique, otherwise we cannot do any task. It will not representative. We need to remove some stop words, and optionally we can use some thesaurus, so we can form phrases. If you form phrases, maybe we actually don't need to remove stop words, because if we use phrases, the phrase will make sense when it contains the stop words. But for phrases, we will have another requirement for our data. What is this requirement? The same as for endurance. The data must be very big, right? Because there's no point to extract every phrase once and get uniform distribution among all the phrases. Just it won't help us. Most of the cases won't help us. And then we do the same for query, of course, because if you have query different from all the other data, then we cannot really match it. So you will have query, you will have document, and you can get some similarity, which, for example, can be just multiplication, the element-wise multiplication, or it can be so-called cosine similarity. And there's other similarities, like Euclidean distance or some Chebyshev distance. So the selection of distance actually depends on task. And sometimes you come up, you just try all the distances and see which one was better. And then try to understand why it's like this. Sometimes you have some initial assumptions, so you select some distance for our computer task. So here is an example, right? We have a query, which is in red, and we have another three documents. And the document representation is a stamped word vector, you can see. And then after we stem it, we can see the occurrence of certain words in the documents. So first of all, in query, first one occur once, and second one occur once, and all the others are zeros. First document, first one time, second two times, and so on, because we can normalize it. But it doesn't really matter. And you have two more documents with a similar representation. So if you apply simple similarity, which is just multiplication of the task, we will see the similarity between first query document, and first document is 3, and another 2 is 1. So what we can conclude from this?
First document is more relevant.
Yeah, more relevant. So it will be the first in our output list. How to handle another 2? Which order you output them? Actually, we maybe need to change the distance, maybe make it more complicated. Or we can need to consider some additional aspects, right? Because it's quite often we have some very similar result of similarity measure, and after that we don't know how to arrange. And in fact, for final user, it's very important because user can see, for example, 10 pages, 10 links in the output page, and it can be 10th and 11th one. He may not go to the second page. And it's actually quite important how we arrange documents and make the most relevant between these two being closer to the top of the output list. Otherwise, you may not recommend to user something he really needs. Yeah, and as you say, yeah, first one is the most important. So, the most relevant. Let's go to classification. Retrieval is, I guess it's clear after the retrieval is quite simple. The basic version of retrieval is quite simple. So those one who work information retrieval, maybe they can add something here. If you have any ideas.
Not now. I suppose it's better class attack.
Okay. So another one can be text classification. So as we mentioned before, classification is assignment of the documents to certain labels, to certain types. So we have some M categories and N documents. And N must be much bigger than M. Why?
Because otherwise it's not classification. So the idea of classification is to work with to use different patterns to work with some class of documents. If you invent patterns for each document, so you won't use your energy wisely. So it's much better to make some specific patterns, and the number of these patterns should be limited. But the difference between the classes should be big enough to use different patterns.
Yeah, actually the similar reason we need to have enough samples, otherwise we overfit the data. And in fact, it's one of the most common ways, one of the most common reasons why papers are rejected in Quantman, because people do evaluation based on small data sets. Why data sets are small? Just because it's difficult to get big one, together with ground truth and with everything. And since all of us computer scientists, we are good at developing different cool features, we come up with some very big feature vectors. Sometimes it's comparable to the number of samples we have, like 1,000 feature vectors from image, right, from image concepts, and thousands users to use it. And yeah, and it doesn't work. So that's why people usually use PCA or some other techniques to try to map it to hierarchies from ImageNet. To make it reasonable. So don't do it in your papers. It's not a good way. Try to come up with something small. And possible applications is, for example, align some subjects to some stories. Just like this. Categorization of news. That's what actually Bloomberg do. They take all the news, fill it in 1,000 classifiers of different categories, and just give you categories of each news. And after that, they categorize everything, and that person can subscribe only for stocks in sports in China. And very likely he will get news just about stocks and sport companies or whatever in China. Just because they have classified for China, for sports, and for stock. Okay, yeah, also we can for stocks and so on. So another can be categorizing of something, right? For example, detecting spam. In fact, spam detection is one big research area many people work on. how to detect spam, or how to detect some robots or not real image. I guess Ivan was working on this recently because I know the research was something related to detecting the Twitter accounts which are not actually people, right? So, and there's many variations for this type of research. Opera screen is some catalog of documents, I said like longer too. And you have many machine learning tools. You have nearest neighbors, and you have some bias, probabilistic learning, and you have some decision trees, and you have neural networks, and regression analysis, and so on, so on, so on. And actually they belong to different families. One of them are purely regression based or something like this. Others are probabilistic. So, and for this we can use single terms as a features, or we can use some relationship between terms. And yeah, as I mentioned, that we have really high dimensionality. And for example, for neural networks, there's a problem, right? So if you want to, I'm sure to do this start the neural networks tutorial, or it's the first day is today. The neural networks tutorial.
Well, they started yesterday.
Oh, okay, so maybe they mentioned that neural networks are nice, but they need a lot of data to train well. So if you have some, if you have some dimension d, which is fitting, you at least need to have 2 d² good samples to be able to train it well. You know, a good example is images, right? So the input is actually high dimension. Usually they fit in images in a row, but you don't really pre-process the features. So just imagine how many images we need to do to train some concepts and so on. And another issue, how to reduce this dimension, right? We need to do some feature selection for these features that we leave will have a huge influence on the target label. And the time those ones you remove, usually you don't really influence it. So it will introduce bias, so we need to get rid of it, otherwise it will just make everything worse. So basically, hypothetically, the difference between information retrieval and classification is like this. Retrieval retains all non-trivial terms, and we can use ADF to select all the rare terms, as I just said before. But at the same time, for classification, for text classification, for other classification, we need some common features. So we use document frequency. So it's actually very different at a certain point. And that's why it has two common images. So what is document frequency? Basically, it's number of documents containing term T, at least once. And information retrieval gives a higher weight for terms with low document frequency. Why? Because if something contains almost no documents, why we need this term? It's not really distinctive between different documents as compared to our query. So how about classification? Is it used? Does document frequency use classification for absolute? Document frequency, is it important for classification?
If document frequency is high in some certain documents, and maybe they belong to the same class.
Yep, that's the basic assumption. So text classification actually prefers terms with a high document frequency. And that's basically the difference. Because rare terms are not really informative for classification tasks because they will not appear if they appear in training sample, they will not appear in testing sample. So when you here is the high frequency and the low frequency terms. And what we can do, we can just use the terms with document frequency higher than certain threshold. And that's also a way to select top key terms in our back of words content classify. And sometimes we can actually compute this threshold for each category. So advantages of this is quite simple and scale well. Disadvantages ad hoc. And it's kind of heuristic thing. So nobody really know how to select it. So other term selection methods is co-occurrence probabilities of a category of term. Basically, it's related to correlation of the term at the category. And this one is favors some rare terms. So, in fact, when we do correlation-based feature filtering, we don't want to have features, similar features in our feature set, which are actually correlated, because it will be two different features, the model may be confused, and in fact these two features will represent the same thing, so we usually remove one of them. So it's important to do some correlation analysis. I'll talk about it later. And we have some term strengths. So this is how commonly a term is likely to appear closely related to the document. And it is basically a global measure. So it's not category specific. And yeah, and I guess Ms. Lady not here today, but yesterday we mentioned that some projects like principal component analysis could be, and it's widely used, but it's already not the feature selection approach. It's already related to projection of our features to some another latent space, which is supposed to be more distinctive and more representative, because this is based on eigenvalue decomposition, so you just pick up the highest eigenvalues. So they will be related to each other. That's why we assume that they are not correlated and they are more distinctive and they are easier, nicer for us to classify. So we can go to some classification methods. I think I'll go briefly because I don't have so much time for it. We have a coffee break right between first two lectures. Water break. So prediction itself is very difficult, especially when we need to do it in the future. And in fact, when we do some classification and prediction, we do it for future because quite often we do it for future just because we have some data set, we will divide it by time and then we predict something for future. For that future which is actually past for us, but for them it was the future. So it's fair to say that it's future prediction. And choice of classification methods is not obvious. And in fact, I told that sometimes it happens that classification is not as crucial as feature selection. So if we pre-process our data well, then we actually can come up with some simple model and it still perform quite well. At the end of today, I think I will show you some example based on data set I introduced yesterday. You can just use some very simple methods and the output parameters will for us. So for feature selection, we need some problem insights. We actually need to understand what is important for us. Rare terms or frequent terms. And we can do some different approaches like TF or IDF to filter out features for certain applications. And for classification methods, classification methods is not too much important, but actually many people will argue, and I understand. And in fact, I would say for research, for publishing, you need nice models, but again, for industry, for some really big data projects, sometimes sometimes some complicated models are just too slow, not scalable enough to work well. So we'll come back to something simple, just modify it regarding to our problem. So just like this. So the system I show you today actually uses quite simple approaches. This is the next system. It uses quite simple approaches for every task and perform quite well because you have a lot of data. You get a lot of data from each subject. Now, of course, we need to do parameter tuning, and we have a colleague in our lab who is doing purely parameter tuning. He's very focused on how to implement some unified approach for too many parameters. So when people publish baselines, these baselines are actually fair. It means they are tuned nearly optimal. So in this case, the approach that we propose, if it outperforms the baseline, it means it's really better than baseline, because sometimes it's another problem. People don't tune the baselines properly enough, and then the approach works better, but actually it's not always the case. Or it can just work better on certain data sets, it won't work better for others. So it's another issue we need to consider. So if you publish paper and you have some baselines, and you didn't spend enough time to tune these baselines, maybe your algorithm is not so good. It doesn't mean anything. We actually need to put enough effort to tune the baselines further. We can claim that our approach is better. Another problem is skilled category distribution. It's always like this, even in data set I introduce. Since social media users are all young people, it's quite often we have a bias towards people from 10 years old, maybe 30 years old, 35 years old, while all others use the social networks quite intensively, but the number of the people is not too much. So one of them, like Ramesh Jain, I showed you yesterday, is super active in social sourcing, but it's not too many people of his age who do the same. So in this case, if we try to do classification of the age of the user, we will face the problem that we don't have too much samples for users who are older than 40 years old. I have a lot of samples for those who are 10 to 20, 20 to 30. We need to handle it somehow. I'll mention later one approach that can actually handle it very well. So the process of classification is as follows. We have some set of training documents, and each document is represented by feature vectors. And we also have a category assignment. So let's say in our case, we binary case, right? So we have this document is either belong to category or doesn't belong to category. So it's a binary assignment. This, for example, can be, if you do image classification, concept learning can be like pineapple or not pineapple, horse or not horse. Or for text example, as we mentioned yesterday, can be National University of Singapore or not National University of Singapore. So just like this. And one issue, this document can be assigned to one or many categories. So sometimes, for example, National University of Singapore can be assigned to first this educational university institute, and second can be assigned, for example, as Singaporean university. I don't know. I mean, it can be many labels and different levels of abstraction for the same document. And as I said, it can belong to many categories. So, and besides this, we also have some supervised learning, which is clustering. I guess I touched clustering a little bit in the previous lecture when I was talking about k-means and hierarchical k-means clustering. I won't touch it today because we don't really use it. But at the same time, clustering is very important because sometimes when we solve our task, we need to do some community detection based on our data. If we detect these communities can give us a lot of insights about users who belong to these communities. And these communities will be clusters. So we detect clusters, and then it actually helps us to predict our final label. So we can gain some high-level interest, for example, people who like arts, and And then among this arts community, we can try to check the occupation, for example, the person musician or some director and also painter or so on. For example, I'm not sure how nice this problem is. Just come out with it just now. It can be like this. So we have this training set of features and a label for this, and we need to pre-process all the training documents, as I mentioned many times before. I won't go to this again. And then we have some classifier, some model that learn or train based on these documents. So after that we can use a train model to test. What is test? Test always means we have some evaluation set. A set of documents for who we know the label, but we don't use these documents for training. That's actually very important. That's quite common mistake for beginners in machine learning or some students. They use test set to train their model, and after that they get just awesome results. Yeah, that's not fair to do it this way. It's an overview, of course. So that's also not the way. You cannot use test set for train set. And when we prepare some data set, we always need to have some data itself. It's not enough. We need to have some labels for training and labels for testing. And the most important, testing labels should be fixed. So if somebody else will use our data sets, he will test their approach with the same testing labels. Then we can compare approaches. Because the testing label can be, if everybody select testing labels, testing samples randomly, then they actually cannot compare, because some can be lucky and select a nice easy one, and opposite can be unlucky and select an easy one. That's why in an assignment I ask you to perform evaluation only on those users who have a field real age. So that's an issue. In this case, we will do all our evaluations only in a certain subset of users, only those who mention their relation Facebook, and then we can compare our solution, hopefully. How many groups formed here? Can you raise your hand? Okay, I see one. I see second one, right?
Oh, that's
Oh,
one.
I have 3 groups. I have 2 in there. Okay, yeah. So I hope we will get some presentations on Thursday. So I don't need to change it to something. It's actually very important, right? To get some insights and data and make some experience, not just listen for lectures. So let's start from the very simple stuff. How many of you know what is KNN classifier? So what is KNN classifier?
Some neural network.
It's kind of machine learning algorithm.
That's very broad. Yeah, it is machine learning.
Okay. So you have number of features, for example, a sort of vector of features, right? And so to classify the n+1, so some kind of and to classify something which is n+1, and if you have n things which are already classified, you have n+1. To classify where does it belong, you just see the nearest neighbors. So if you see that the nearest neighbor belongs to group 2, so you put this thing into group 2.
So you are now talking about a certain case. It's called one nearest neighbor.
Yeah. I mean, so the simplest, of course. the KNN means so you measure according to k nearest neighbors.
And how you measure? So you have K members. How you do it? It's actually many ways.
So for example, you can use some weights for this neighbor. So if the neighbor is the nearest, so it will be the strongest connection. So if the neighbor is a little bit far away, so the connection will be weaker. So you just try to approximate.
Yeah, it's all reasonable ideas. Basically, it works very well. Just like how we say, we have uh, some data points is our training, but actually this classifier is not training. The data itself is already trained model. So we have some data points, which is our test document, right? Then we see the nearest neighbor of this document, and to which category will you classify this point, to green or to orange? To green. And what will be the K for this case?
Number of greens and orange in the radius.
K here is 5.
Yeah. That's the point. It's not number of greens, it's number of neighbors we consider. So we draw a circle around those neighbors we consider.
Alex, a small note that K is usually lazy classifier which do not have a learned thread, but not always, because more complex models have to learn kernel functions. They use scalar trees to make the evaluation of nearest neighbors more fast and precise and so on. So
Yeah, correct. Of course, I'm talking about the very basic one. And all of them have the long story and numbers of publications how to improve it, to make it A, faster, B, more efficient. So just like one improvement can be used, like a gentleman told us that we actually can use a weights and consider the weights of these neighbors. So don't treat them equally in a voting. So not just count number of categories, but actually see how far each of these neighbors from our search point. And this actually may help us to improve, right? Especially in cases when we have a similar number of guys of different categories. So suppose we'll have here similar number of oranges and similar number of greens. So we need to decide which class wins. So then we can use the position in a ranking list of near neighbors. So we decide this document belongs to green category since majority of them are green. And that's the whole idea. So we have this document, define some neighbors among training documents. We have the top similar values. So we can use Kazan similarity, for example. And one of the recent studies in our lab, people was using KNN and they come up with a value 45. Yeah, wherever for different data sets and for different applications it can be different. Just like one of values of near neighbors could be used for all of this thing. And decision rule can be written like this. So this where BJ is a category specific threshold. So you can look through the slides later on the lecture. This one I was also talking about, so we actually need to divide documents and training and test documents. And training set may have 80%, for example, or test set may have 20, or maybe 70, 30, something like this. So we train the classifier on the train set and then validate it with the validation test set. And you can use different evaluation measures like F-weather or, for example, like accuracy, recall, precision, and recall that I mentioned before. So it's also task dependent. For some retrieval tasks we can use so-called DCG measure to extract all the recipes. So this threshold permits a new document to be classified in multiple categories more efficiently. And it doesn't carry offline training in a simple version. It doesn't carry any offline training. And yeah, in a simple way, I guess it's a linear, so we should go through all the documents we have that have a similarity. Only this way we can select those ones who are nearest. Otherwise, yeah, otherwise it won't work. So, how many of you know what is naive bias? Or what is bias classifier? Okay. Anyway, this is another class of approaches. It's a sort of probabilistic one. I also won't go too much in details, but the idea is similar. We just compute the probabilities that some classifier, some training sample, some test sample belong to some category, and probabilities are computed based on training samples. So that will go from a text to something else, and you, for example, have some digit recognition thing. And yeah, and our features could be just pixels. Of course, it's not a real example, and it can be something more interesting. One of features I explained yesterday. Let's say it's just binary features. We have monochrome image, right, which consists of 2 colors. So, and we want to classify it between 5 and 6, or 5 and not 5, something like this. So, in fact, the bias classifier itself, we just need to find the probability of the label given all the features we have. So, the example is what is the probability that image represented 5 given these pixels, where pixels actually are the features. So how to compute this? Ideas? We're going to talk about bias classifier, right? Yeah, okay. So since it's bias classifier, we have bias row, which looks like this, right? We have probability of label given some features, which will be equal to likelihood, which is probability of features given label. The probability of label, which is number of this label occur in our training samples, and some normalization constant, which is joint probability of all the features. I guess all of you have some basic probability theory knowledge. So anyway, here's the idea. So the bias classifier will look in this way. Probability of label y given these features will look like this. According to the bias from probability y6, it will look like this. It's quite simple. The problem is we cannot really explicitly model the probability of features given y, because it's too big, it's too much space. And of course, if we say that all these variables depend on each other, they may depend on each other. You know how to compute the joint probability, right? It will be actually quite big expansion. So in this case, if we say that our classifier is naive bias classifier, what does it mean? What does it mean it's naive? What naive
Make
means?
some simple suggestions.
Again?
Make some simple suggestions about.
It makes some very root and simple assumption, but surprisingly it still works very well. And this never holds, this assumption never holds in fact, but it worked well. And I was doing some competitions 3 years ago in the Yandex data set. We were trying to predict the clicks of user in the search queries. And we tried random forest and other complicated stuff, deep learning, but finally naive bias was the best. Because data was big and yeah, it was just the best. I don't know, it sometimes happens, so it's worked quite well. So what is this simple assumption? How do you think? Why it's naive?
Make uniform distribution for y's.
It's just a sum that all the variables are independent from each other. So we can compute the probabilities in this way. So probability of features given y would be just multiplications of probabilities of each feature given y. So for this we only need 2n computations. Well, the first one, if we really do it conventionally, in deep inside, we have to multiply 2 in power of n minus 1 computations, if I'm not wrong. Yeah, I think so. And then we have some training labels. We have many 5s and many 6s. And yeah, it's supposed to be blue and red, but it's black and white, but it's still monochrome, right? So it will be the same. So actually it's interesting, we can test this approach on blue and red picture by turning it black and white, because all of them will be zeros and ones anyway. And after that, the training is very easy. We estimate P probability of label, which will be the fraction of records, where the label actually is this label, for example, 5. And also we need to estimate the probability of features given a label. It should be the fraction of records where we have this label for each feature. And this one, that's whole training. So that's why it's very fast. It's actually linear. And then you have all these counts. It may happen that for some categories it actually will be 0. And we may apply so-called smoothing. So we'll say that all these counts is actually 1s. And those ones that are bigger than 1s, they will be bigger than 1s, we normalize everything, and you'll get some distribution where each probability will still be something. Because if you won't smooth it, if you get some probability which is 0, it will make everything 0, the whole multiplication 0, and then it will be too easy to decide that some category is not that category, but in fact it could be. So is it clear why we need smoothing? I'm not sure. Yeah, and they use smoothing for LTE that I explained last time. It's a very basic thing, just to make it somehow every time of 0. Because 0 actually makes a lot of troubles for us. Then these numbers can be classified as 5 because it looks very similar to our trained sample, as 6, and something which is supposed to be 2 and doesn't look like 5 and 6, so it will be classified as 5 but with some small probability. Here I just want to say that, yeah, sometimes we actually don't know what that can be. It's somehow more similar to 5 probably, because we have this, but it's still not as confident as in the first example. How many of you know what is SVM? What's the idea of SVM?
Support vectors.
What is support vectors?
Vector which separate one from another is the maximum gap.
Yeah, somehow it's about that. Yeah, but I think you can get it from the name, right? So
Maximize distance between
margins. It's called margin.
Yes, margin.
So that's actually the crucial point, right? If you have something like our data points, yeah, maybe I should add that in slides. You have these data points, how we classify it, right? We don't really know how to classify it. So we can do a hyperplane like this. Yeah, that's two-dimensional space, but it can be multi-dimensional space, it will be multi-dimensional hyperplane, doesn't matter. We notate this for the multi-dimensional case. But it will be with optimal separation, how do you think? In this way. Is it optimal or not? Because the idea is, yeah, we separate it somehow, a hyperplane, and then we use these two rules to decide either it's one category or another category. But problem is we can do it also this way, right? But fair enough. And we can do it this way. It's still okay, right? And also we can do it this way. And many other ways. So we need to introduce something new to help us. So suppose we separate them in this way, then we will get some data point which will be misclassified. So how to avoid this? Any ideas? Actually already mentioned. Theoretically, we can have one more paper plane, we can make sample, and we will still classify it correctly. But in SVM, we will have this solid line, which actually called the margin. So we will have hyperplane, and we will compute the distances between nearest points to this hyperplane from our data. And we will draw a hyperplane with a maximum margin, with a maximum of this distance. We will maximize it. So in this case, we somehow get the optimal solution on this. Okay, this is a linear case, right? We have also non-linear SVM and other variations, as you say. In linear case, it will be like this, right? So what will be the support vectors here?
This line.
Again?
This line.
So this. Actually, we will consider on design. All the other data is not too interesting for us. For us, the most important, those guys call them a border, because we think about them the most, because they are responsible for misclassification. Yeah, and so we maximize the margin, and it's good. Somehow it's good. Probably the so-called PAC theories probably accurate enough, such as this. So it's supposed to be good. It's supposed to be, and since it's a convex model, we actually can maximize it. And then you'll get optimal solution of the linear case of this problem. As implies only support vectors are important, so these 3 points in our case are important. And it works very well. I would say SVM is quite old approach, but you can still see a lot of papers, and even in my paper, in my recent paper, we actually use SVM as one of simple baselines to compare our approach. That's because it works well, and in fact, many of all these current models that are deployed for machine learning, they somehow similar to SVM. Still is a maximization of this margin, or it will be some other cost function, least squares, when you just fit the data. There can be some logistic laws, with many regularizers, and this basically is the difference between different models, how you regularize this model. And then you optimize it, go with convex, optimize, and get some solution. So that's why SVM still perform well. In fact, in our last lab meeting, somebody introduced new approach. And then approach was the best, but the second best was SVM, and all the complicated models were actually worse than SVM was abilities. I guess it was not linear SVM, but doesn't matter. The idea is similar. So the margin can be computed just like this. Actually, you can go to Wikipedia or to original SVM paper and really see the derivations, how it really works. So correctly classified are examples are in first case, and for the second category, which is -1 in the second case. And we also have a constraint. It's like this. It's a linear constraint. So I think I won't go too deep in details because I already exceeded the limit. But the idea here is we need to minimize this problem. So we have quadratic problem and a linear constraint, and to minimize it, we use so-called Lagrangian multipliers. Do you know what is Lagrangian multipliers? Anybody knows? Yeah, basically it's yeah. So this is a way how we incorporate constraints in our model to still keep it convex. After that, we can use one of various methods to optimize the solution. One of them can be gradient descent, for example. When we just have our cost function, and we compute the gradient, which is the direction of growth function. And if our function grows, in some direction, like here, we will go the opposite direction with the sum step delta. And there's various approaches how to select this delta, because if it's like too big delta, we may go to here and actually it will not converge. And this is completely one more topic. Maybe next year maybe I can just devote everything to this, because it's a very big area and a lot of people do this. Actually, it's very important to be able to build this model, because most of the models, state-of-the-art models, are somehow convex and optimized in certain ways. And this requirement for publishing a nice conference that are related to machine learning or information retrieval and so on. Yeah, I didn't mention actually, our problem can be rewritten as a dual problem. Duality is one of the cornerstones of the whole optimization theory. So actually problems can be reformulated as a dual problem. So these dual problems sometimes are actually much easier to optimize as compared to the original one. So the dual problem will look like this, and you have alphas, and after that we'll maximize it. So yeah, I won't go to detail, we can just read it about it. It's actually not so complicated. So the basic idea is to find the optimal hyperplane in terms of the boundaries, in terms of the margin around this hyperplane, and then use this hyperplane to separate our test samples. So the margin of separation is twice distance of nearest point to plane. An optimal hyperplane is hyperplane is the largest margin around it to the points. And support vectors is all these samples that lies on margin. And this decision surface is actually defined by the support vectors. And it's guarantee somehow to find the global solution. And we have many other stuff related to SVM. For example, sometimes our data is not so nicely separatable as in the picture as I showed. So in this case, they introduce so-called soft margin, which expands the initial equation of SVM. So this soft margin allows some points actually be misclassified, and we estimate the number of points will be misclassified, and we will also regularize based on this number of misclassified points. So in this case, we will be not so strict in deciding which label it is. And another way, sometimes our data points are not really linearly separable. So what we can do, we can just use some function like Gaussian to map it to some high-dimensional space. And we think that in that space it could be separatable, which is quite often helps. It's called kernel of SVM. The only difference in equation before, the dot product will be replaced with the multiplication to this function, to go through this function, in fact. And the selection of kernel is another tricky process for different applications, different kernel can be used. But overall idea is like this. And there's many SVMs. So I would recommend you use SVM and naive biases like your first tries to check whether some task is reasonable for some data. We can actually use these simple classifiers to try to get some results which are higher than random. If your results are higher than random, it means you at least have so-called weak learner. It means your task is somehow reasonable. In most of the cases, it means it's reasonable. So after that, you can start working on some more complicated models that leverage on more problem-specific aspects and probably outperform the SVM, which is actually not so easy. It's not so easy to outperform SVM. So, sorry, I'm a bit late. It's quite heavy chapter. So we recall some frequent features that we use from the last lesson, right? We say that frequent features are useful for classification, while for retrieval we usually prefer array features that can be used with document frequency and non-document frequency respectively. And we also introduce some machine learning approaches like ANN, PIs, and support vector machine. Why they exist three just because they belong somehow to different families. And all of them are basics, right? So first it's a lot of expansions of these approaches used. Yeah, and the next will be about source fusion. So I guess it's a water break, coffee break, and